Hello everyone, welcome back to our YouTube channel. The topic that we will discuss today is equipotential surface. So first of all, let us understand what is this equipotential surface. An equipotential surface is the locus of points at which the potential due to a charge distribution is same. So first of all, let us consider a positive test charge Q located somewhere at this point. Suppose if we draw a surface like this around this charge plus Q, so each and every point on this dotted line will have the same potential, and this surface now represent an equipotential surface. Suppose this is a point A and this is a point B. The distance of a point A from this plus Q, say it is R, and the distance of a point B from this plus Q, it is also R. As we know, potential at any point due to a charge Q is represented by V equal 1 by 4 pi epsilon naught then Q divided by R. So as we can see from here, this point A, it is at a distance R from plus Q. So suppose the potential at A is VA, then this one is represented by 1 by 4 pi epsilon naught Q, and the distance of this point A from plus Q, it is R. So similarly, this point B, it is at a distance R, so the potential at B, it is equal to 1 by 4 pi epsilon naught Q divided by R. Suppose if we choose another point, say C, then another point D, so all points will have a distance equivalent to R from plus Q. So each and every point on this surface will have the same potential. As we can see from here, for these 2 points A and B, what is this? VA is equal to VB. So this surface now represent an equipotential surface. Suppose if we draw another equipotential surface. Suppose this is a point A, the potential is VA. If we choose another point, say X, on this surface, which of the point will have more potential? If we draw a line from here to this point, suppose if this one is R and this one is capital R, the potential at a point capital X, it will be Vx. So now this Vx is 1 by 4 pi epsilon naught then Q divided by capital R. So the potential at this point X, it will be Vx, and that is equal to what? 1 by 4 pi epsilon naught Q divided by capital R. As we see from here, the distance of a point X is much larger than the distance of a point A from this point O, say. So clearly from here, R is less than capital R. This means that VA, it is greater than Vx. Why? Because this R, it is smaller than capital R. So now, since this is plus Q, the direction of the electric field lines will always in this direction. They will come out from that point. From here, we can conclude that the potential keep on decreasing. The potential keep on decreasing in the direction of electric field. So one more thing. Suppose if the spacing between these two equipotential surface, say this equipotential surface 1 and this another, it is 2. Suppose the spacing between these two equipotential surface, say it is dr, then what is the relation between the electric field and the difference in the potential between these two surfaces? We have discussed earlier that the electric field, it is equivalent to minus dV by dr. The negative sign indicate that as R increases, V decreases. That means as we move away from this point O, the potential keep on decreases. Suppose if dV is fixed, then what is E? E is inversely proportional to dr. Or we can say that dr is inversely proportional to the electric field. This equation represents that as the field becomes strong, that means E increases, then what will happen to dr? Dr will decreases. So this equation explains the grounding of equipotential surface in the region of strong electric field. So having an idea on the equipotential surface, now we will discuss some of the characteristics of equipotential surface. So the first one is work done in moving a test charge through an equipotential surface is 0. So let us consider a charge plus Q, and now if we draw a surface like this, each point on this surface will have the same potential. Now this is a point A and this is a point B. The distance of a point A from plus Q, it is R, and the distance of a point B from plus Q, it is also R. So potential are equal. So VA equal VB. And now if we want to move a test charge Q0 from A to B, that is WAB, in moving this test charge, this WAB is a work done in moving this test charge from A to B, and if we divide this one by Q0, so this one is nothing but the difference in potential, VB minus VA. So since VA equal VB, then WAB divided by Q0, this one is equal 0, and this implies that WAB is equal 0. So this shows that the work done in moving a test charge through an equipotential surface is 0. Next, electric field is always perpendicular to the equipotential surface. So again, let us draw an equipotential surface. If we mark this one as A and mark this one as B, this one is R and this one, it is also R. And now suppose if we move this charge from A to B, say let dl be the distance through which a charge q naught is moved. So since this is a charge, this q naught will experience a force at any point on the path. As we know from here that this WAB, it is equal 0. So this WAB, it is nothing but Q naught E dot dl. This one is equal 0. So this implies that E dot dl, it is equal 0. So what does this mean? E dot dl is equal 0 mean E dl then cos theta, this is equal 0, because if you have two vector E and dl, or if you have two vector A and B, A dot B is nothing but A B cos theta. So similarly here, E dot dl is equal 0, it means E dl cos theta equal 0. E cannot be 0, dl also cannot be 0. The only possibilities to be 0 is cos theta is equal 0. So cos theta equal 0 mean theta equal 90 degree. So what is theta? Theta here, it is the angle between E and dl. So this means that E, it is perpendicular to dl. So since dl, it is on the surface and E is perpendicular to dl, hence from here we can say that electric field is always perpendicular to the equipotential surface. So now we will draw the equipotential surface for a uniform electric field. In a uniform electric field, the strength and direction of the electric field is same at every point on it. Suppose this line represents a uniform electric field, and here we want to draw the equipotential surface due to this uniform electric field. So as we have learned earlier that E is equal minus dV by dr, this negative sign indicates that as R increases, then V decreases. So as we can see from here that this electric field is uniform. So this implies that dV by dr is equal to constant. This means that dV is proportional to dr. So if this is one equipotential surface, say the potential here at each and every point in the surface, say it is V1. And then if we draw another equipotential surface, say it is V2. And then if we draw another equipotential surface, say it is V3. So remember, if V1 minus V2 is equal to V2 minus V3, then this spacing between these two equipotential surface are also same. dV is proportional to dr. So this equation shows that if the difference in potential between these two surfaces are equal, then the spacing between these equipotential surfaces are also same. One more thing, as we have mentioned earlier, that the potential is keep on decreasing in a direction of electric field. So this electric field, it is in this direction. So therefore, here we can say that V3 is less than V2, it is less than V1. Now we will draw the equipotential surface for an isolated point charge. So let us consider a point charge, say it is plus Q, and suppose we draw one surface around this charge, and again we draw another surface around this charge. So the direction of the electric field lines of force is always like this. So we know from the relation E equal minus dV by dr, this negative sign indicates that as R increases, V decreases. So if dV is fixed, then E is inversely proportional to dr, or dr is inversely proportional to E. This equation explains the grounding of equipotential surface in the region of strong field. So therefore, here as we go away from this point, the spacing between the equipotential surface keep on increasing. So if the spacing between this surface and this surface, this, as we go further, so this surface, this spacing keep on increasing like this, and then like this. This perpendicular distance between these two surfaces keep on increasing. So from here to here, this one is smaller, so is bigger, then it keep on increasing. This is because of this equation. Now we will draw the equipotential surface for a system of 2-point charge. So first of all, let us consider that both the charges are plus. So since this is plus, Then the electric field lines of force will come out, say like this, like this, like this. And then this like this. Okay. So now this line, solid line with an arrow, represent the electric field lines of force. And now if we draw the equipotential surface, it will be like this, then like this, and then like this. Like this. Similarly, if we have two charges, one is minus and the other is plus, then the electric field lines of force, since this one is minus, then the electric field lines of force will entering like this. Like this. So this one is positive, it is come out like this. Like this. So like this. Like this. So these solid lines with an arrow represent the electric field lines of force. For positive charge, they are come out. For negative charge, they are entering. If we draw the equipotential surface, suppose this one is equipotential surface, and then the other one, this is an equipotential surface. This one is an equipotential surface, and this one is an equipotential surface. If both the charges are positive, then we have this dotted line represent the equipotential surface, and have one is minus and one is plus, then the equipotential surface is represented in this form by these dotted line. Remember, the equipotential surface due to the two charges are obtained by adding the potential at the point due to the two charges. Now, let us solve this question. Figure shows some equipotential surfaces. What can you say about the magnitude and direction of the electric field? So, solution. So, for simplicity, Let us consider only two surfaces. Say this one is y, this one is x. Say this one is one surface which is 5 volt, and this is another surface which is 10 volt. So here it is 30 degree. So this one, it is also 30 degree. We have learned earlier that the potential keep on decreasing in the direction of electric field, and also the electric field is mutually perpendicular to the equipotential surface. Therefore, if we represent the electric field, we have to represent by this line, like this. Remember that this angle, it is 90 degree, and as I have mentioned earlier, the potential keep on decreasing in the direction of electric field. So therefore, as we go from here in this direction, the potential from 10 volt decrease to 5 volt. So where's the direction of the electric field? It is in this direction, and this angle, it is 60 degree. This is the answer to this question. The second question says, a positive charge plus 2q is located at a point. What is the work done if a unit positive charge is carried once around this charge along a circle of radius 4 cm about this point? So suppose this one is plus 2q. If we draw a circle which is of radius 4 cm, as we can see from here, each and every point on this circle, their potential are same. So hence, the work done in moving a unit positive charge along a circle is equal 0. So work done is equal to 0. So that is the work done in moving a unit positive charge around this circle.